Joshua Vogelstein is another of our guests from Johns Hopkins University, and I'm guessing it is no accident that his talk is following from Kay's on fixing artificial intelligence via natural intelligence. He is an associate professor within the biomedical engineering area at Johns Hopkins with joint appointments in applied maths and statistics, computer science, electrical and computer engineering, neuroscience, and biostatistics.
Great.
Fabulous breadth of
Thank you.
expertise there. Thank you. Please tell us how we're going to make artificial intelligence more intelligent.
I will try. Okay, thank you so much for the kind introduction. I'm super excited to be here. Just want to just tell you one little anecdote about this morning to tell you like how much I really cared. I ended up waking up my COVID-y wife this morning, who was taking care of my COVID-y son, to care for my baby so I could come here and be here for the talk. So like I'm pretty committed to being here. I'm really grateful for the opportunity, and I've really had a great time yesterday talking to everybody. I'm excited about what is going to happen now. So the title of my talk is Fixing Artificial Intelligence with Natural Intelligence. Obviously, I'm not actually fixing it in the next 40 minutes. Like, it's a bit of hyperbole, but anyway, that's fun. Okay, so I was paying attention yesterday when we did this experiential learning exercise, and I thought, let's do one now in my talk. We can take a few minutes for that. So everybody has a pen and paper in front of you. I'd like you to do the following. I'm going to give you instructions. Don't ask any questions out loud, because that could ruin it. Just do the following. Imagine you're flipping a coin 10 times, and just write down the sequence that you get. You could use H and T, or you could use 0 and 1, or something else if you want. Just 10 binary number. Okay, and when you're done, just look up so I know you're done. Great. Great. Okay, that's the first experiment. I'm gonna explain the results in a bit, but I first want you to do one more experiment, which is the same thing, but now I want you to imagine that coin has a 75% chance of landing on heads. Again, 10 flips, but 75% chance of landing on heads. That's harder. Ike's pleased with this experiment, it seems. Okay, just say everybody's done. Now, just want to get the results back. So raise your hands if on the first one you wrote down exactly 5 heads. You're so proud of yourself, Mercedes. Okay. Raise your hand if on the second one you wrote down 9 heads. Nobody? Okay. So raise your hand if on the first one you wrote down 7 heads. Raise your hand if on the first one you wrote down 4 heads in a row. 5 heads in a row? You're not sure?
I wrote down 10 zeros.
Really?
Yes.
That's cool.
It's in there somewhere.
It's in there. It's 1.5 to, it's small. 0.5 to the 10. Anyway, so the point of that experiment is, it turns out, like the probability of getting, say, 9 heads when the probability is 0.75 is about 18%. So in the room, if we were actually pretty good random number generators, about 18% of you would have done that. I think no one did that. Maybe Clifford did that for the first one, but anyway. And on the other one, the 0.5, like, the statistics are slightly complicated, but some people should have gotten 3 in a row, 4 in a row, 5 in a row. I didn't quite count. Maybe you guys did that one pretty well. But the next one, it sounds like, as a collective, we really did a relatively poor job of sampling. This is really just one of the simplest inferences one can make, is flipping a coin. It's just not fair. right? And so the point of that exercise, I just want to convey to us that like we talk about intelligence and general intelligence, artificial general intelligence, and like we're not that great, right? Like that's basically the simplest possible inference you can make, and we struggled with it. And it's not just the people in this room, to be clear. There's lots of results. People are bad at this in general. As it turns out, Wolfram Alpha is perfect at it. I don't know if anyone knows Wolfram Alpha, but it's 10, 20-year-old technology, more or less. It can compute binomial probabilities perfectly, instantly. But what about LLMs? Everyone loves talking about LLMs. There's an article published a few months ago saying they exhibit the spark of general intelligence from my friends at Microsoft Research. So you can ask an LLM to do this. Generate 10 Bernoulli trials where 0 is generated with probability 0.5 and 1 with probability 0.1. By the way, I asked ChatGPT yesterday again just to check. It hasn't like changed a lot. And you can ask in particular on open source ones. I refuse to pay for the other ones because I'm not paying them to do experiments on them. Like they can pay me if they want. But I probably won't take their money. But anyway, it turns out Gamma, Lemma, 2 open source ones, they can't do it. They're just as bad as you guys and me and other humans. So it should have kind of been peaky around here, these plots. This is the distribution of, I told it to do it like many, many times, right? And so how often did they get, on average, 50% of them are zeros and ones? And the answer is they tend to make this assumption that probably you all made on the first question. I didn't say whether the coin was biased or not in the first one. And Clifford may have assumed it was extremely biased, and then he was exactly right, or not. But the point is, if you tell it that there's bias, it still can't do it. So if you're worried about like an AI apocalypse, I just want to point out like it can't do the simplest thing basically imaginable yet. And like, that's not super worrisome from my perspective. Okay, so with that in mind, now I have you guys thinking about what it means to be intelligent and how bad we are at it, and AI is it. I want to get into more about the learning stuff. So the executive summary from what we're going to go from here is, what is learning? I'm not going to tell you the answers right now. I'm just going to tell you the questions. What is learning? How did we get it? How do we model it? What's wrong with our model? How do we fix it? And now what do we do? So that's a short summary of the rest of the talk. I want to start with this video. This video is of a single-cell amoeba. And you might think, man, humans are like really good at learning and intelligence. But I don't know if you guys have ever tried to hunt. But these guys are pretty awesome. This is a single-cell amoeba. It has a little harpoon that it coils up. And I'm going to show you a video of it hunting. Boop. And now it takes that other little guy away. Did you catch it? You want to see it again? Okay, watch carefully. This is the food right here, and this is the amoeba that shot a harpoon, now it's carrying it away. Okay? That's a single-cell amoeba that learned over evolutionary time that it can get food better by hunting than it could with photosynthesis, which is what its ancestors did. Okay? That's an example of biological learning. Some of you have seen this video before, I'm guessing. This is squirrels learning. I'm just going to show you how natural it is in the animal kingdom. Here's a squirrel. This is the backyard of a NASA engineer who became a YouTube influencer by taking videos of squirrels. So, yeah, he built this whole thing, and what's that? The Squirrel Ninja Warrior course, yeah. It took weeks and weeks for the squirrels to learn how to go all the way from the start place over to get where the nuts are, because it really likes walnuts. And some squirrels learned it by trying. That's the guy. He's a manual override, so it's safe. There's a lot. This is like a 20-minute video, and he also has a follow-up video. But the point is they learned. Some of them learned by doing it. Others watched the first squirrel do it and then could do it. There's some safety things in here. It shows also how they learn to always land on their feet, which is cool. Anyway, the squirrels are very happy at the end. So that's squirrel learning. This is a video of human learning, and this is something called reversal learning. If you guys have ever ridden a bike, it's probably fine. But have you ever ridden a bike where the handlebars are reversed? right? So you can make it so when you turn to the left, the wheel goes to the right, or vice versa. And as it turns out, when you know how to ride a bike and you get on one of these things, you feel like a complete idiot because you can't go anywhere. Like, you'd think I should be able to go like a foot. Nope. You like fall instantly. Like worse than if you had never learned how to ride a bike. This is a video of this dude going around the world just showing people how horrible they are at this thing. And it turns out you can eventually learn to do it, and then you can learn to switch back if you want, but it's quite hard. Okay, so learning. I just gave you a bunch of examples of learning in biology, and what I claim is a very general colloquial notion of learning. It's the ability to use the past to improve future performance, and that's it. You don't need all the fancy schmancy AI stuff. You don't even need to do it within a lifetime. You just need to there be a goal and a metric, and then you improved it. And what I claim is it's an evolved property. It's a natural phenomenon that we've all experienced personally in our lives. And it evolved because the past is related to the future in certain ways. If it was identical to the future, learning would be one kind of thing, but it's not. It's similar to the future. If it was independent of the future, learning would be totally useless. There'd be nothing to learn. Right? So learning is an evolved, useful property because the natural world has this property that the past and the future are related in various ways. Okay, so now we know that. But now we talk about learning from an AI context. So my PhD is neuroscience, but I really do a bunch of artificial intelligence. So we talk about learning and prove theories about learning all the time. And AI, I just want to point out to you, what we call learning, it's a model of this real thing in the world. It's not the thing. Like, we are all learning, and AI is doing a thing that models learning. And if you go back to like the Dartmouth conference when AI started, people were pretty clear about that distinction, actually. Since then, people have developed multiple formal definitions and models of learning. One's called probably approximately correct. That's the main one. We'll talk about in a little bit. Another is online learning. Another is reinforcement learning. And George Box is a famous statistician, and one of his most famous quotes is, "All models are wrong, but some are useful." And so let's take our models of learning. Here's actually the leading AI model of learning. As it turns out, most people don't know this. It's from a paper in the 30s. You can read the title. My Italian is poor, but something like Approximating Empirical Probabilities seems to be what the title is about. This is a paper by, there's a book by De Finetti. There's two authors wrote two papers, Glavenko and Cantelli in 1933. And my Italian is poor, but resulta is clear, right? Like, that word I got, it's on page 6. And here's what it's saying. If you have some distribution observed in the world somehow, this thing, F sub h, is your empirical estimate of that distribution. And what it's saying is, if you get enough data, your estimate converges to something close to the truth. It's a result from 1933. If you read the more recent stuff in AI, like from the 60s with Vapnik, they cite this work. They're very clear. This is basically the foundation, and they're generalizing it. So this is 90-year-old result. Almost all of AI is generalizing this result. Okay, now, it's a model of learning. So let's talk about, is it useful and is it wrong? So yes. How useful is it? Well, basically, if you look at the entire mainstream deployment of AI in the world, including LLMs and ChatGPT, almost all of it is based on this. The algorithms were developed based on this theory. Almost nothing is really using reinforcement learning or online learning in practice. It's essentially the main theory, the main model. However, we know the assumptions are wrong. One of the assumptions is the data are IID, which means identical and independently distributed. What that means is the distribution of the past is identical to the distribution of the future. And that is, of course, false, because things happen in the future that didn't happen in the past in various ways. Another goal, which we're not going to talk about as much here, another assumption is that the goal is fixed. So the loss function in these things is just a constant. It never changes. In reality, say me as a human being, when I was little, I really wanted breast milk. Now I'm okay with it, but I actually want steak more, right? As I get older, I'm going to want other stuff more, maybe like Metamucil or something, right? The point is what we want changes over time. Our goals are evolving in time because we're natural beings. And that's just not in the model. So there's two ways in which it's wrong. We're working on both. I'm going to elaborate a little bit more on the first one.
Question down front.
Yes.
I'll use the term unlearning. Is unlearning a form of learning then?
Yeah, it's a great question. We have a paper about learning and forgetting, and I claim it's totally fine. Like the general definition I gave you, if you're using the past to improve performance, you're learning. If you use the past and you actually make your performance worse, I call that forgetting. Yeah.
Where does the concept of dynamic machine learning fit in, whereby you build up a corpus as things progress, and you don't have to train anything initially, it just naturally evolves?
Keeps updating. Yeah, it's a great question. And the answer is, it doesn't fit at all in this theory. Like, pack theory, as you'll see, has no dynamics and no time.
You should have come to some of my earlier talks.
I would love to. We can talk more later. Okay. So here's the simplest model ever, as we already experienced, the binary coin flips. Here's a sequence of 20. This was, the probability was like 0.75 of being on a 1. So you can see the x-axis. Oh, shit, that was the wrong button. Sorry. The x-axis is time. This is just multiple flips. The y-axis is whether it's a 0 or 1. And computers can do this very well right now. All of machine learning is a glorified version of this. What I mean by that is, let's say you're trying to predict the next word. Okay, so there's not just two options, there's many options. But what do? You try to estimate the probabilities of words, and then you just guess which one's the most likely. Same thing here. If we got this data, we would guess the probability of a 0 or 1, and then if we got the next, they asked what's the next one, we would just guess whatever we thought was most likely. So machine learning is a glorified version of just this thing, and that's what it does extremely well today, as long as everything is constant. However, now here's a slightly more complicated scenario. We didn't actually do this one, because I don't know why. Anyway, we didn't do it. But here, on the even flips, the probability of a heads is 0.75. And on the odd flips, it's 0.25. So over the entire time period, the average probability of landing on a heads is 0.5. So if you just did machine learning, whatever you want, do the fanciest thing in the world, you gave it this data set, it would think the probability of landing on heads is 0.5 forever. Because it doesn't have this notion of dynamics that Mike is talking about, doesn't have time in there. Okay? So I'm going to present a simple way of dealing with that, essentially. So while you might care, I don't know if you guys remember the Google flu trend fiasco, but Google flu, they decided this project that they were going to try to predict flu. It's very important, actually, for the hospitals, because if you get the flu, you go sometimes you need oxygen. And there's not enough oxygen for everyone that has the flu to get it at the same time, actually. It's actually why the ICUs have this, the number of beds is based on the expected flu counts in those cities. Because that's where you need them, because that's where you get oxygen. So it's an actual real problem for hospitals to be able to predict who's going to have the flu when and make sure the oxygen is distributed. Google tried to do it. Google has like the most data in the world, and the biggest computers in the world, and arguably the smartest people in the world, all working to make them more money. So they came out with the Google flu trend thing, where they're trying to say, oh, we can predict who's going to have the flu where better than, say, the CDC, which has been doing it in the dumbest possible way, a version of what Ike was saying, which is you just look at what happened last week, you say probably about that next week. Pretty good, right? Okay, so they make their model, they stop training in like about 2011, and then we just look at how well it performs over the next few years. And what you'll see is it's high, 100 out of 108 weeks. So it's kind of like Clifford. We're just like always one, no matter what, or always 0, no matter what. Google thought it was way too high. It was completely unbiased and inaccurate. Also, it was hugely wrong. Like there was periods of time where its error was 150%. The dumbest thing ever was never that bad. So it's much, much worse than basically nothing.
Excuse me,
Yeah.
question. Are the actual flu counts up on there? It just says lagged CDC and Google flu plus CDC.
Yeah, no, this is just the error. Sorry, the y-axis is just the error. Yeah, I'm sorry to make that more big. Yeah, Ike?
So if the gold is the Google flu number, if the model could learn from the fact that it was wrong there,
Yeah.
it could get better over time.
In theory, it could. This model that they use, which is the case for almost all machine learning models, has no notion of time. So you can jerry-rig it to try to update it sequentially, but then there's no theory that says it should work or anything like that. So, but I'm going to tell you how to address it shortly.
Another question about this. Is it more important to be not wrong on the downward side than it is to be not wrong on the upward side? In other words, is it a better predictor if it overestimates than if it underestimates?
I don't know.
Well, it's a practical application. If you underestimate, you kill people. If
Yeah,
you
yeah.
overestimate, you have too much supply.
I don't think you. Yeah, I don't know the answer, but what I would say is,
Limited.
I'm not gonna. I don't have anything to say about false positive rates and false negative rates in this particular talk, but I do have a completely different talk where we talk about how they do that completely wrong also and how we fix that. Happy to explain that to you as well. Okay, here's another reason why you might care. Intelligence is what makes us us. We literally call ourselves Homo sapiens. It's Latin for intelligent man. Sorry, I didn't make up the term. But like, it's kind of a defining thing, and I think it's worth understanding. And part of that is learning, and so our models of learning, insofar as they lead to problems in AI, fine, but they also lead to problems, I think, in understanding ourselves. And that's actually why I care. Okay, so here's this book published about 10 years ago by Leslie Valiant. If you don't know who he is, he won effectively it's called the Turing Award. It's basically the Nobel Prize for computer science. Earlier, other people who won it are like Yoshua Bengio and Jan LeCun. And so he's kind of a big deal in computer science. He kind of invented, probably approximately correct, although technically he just cited the 33 paper, but he did push it further. And he's like one of the main people in the field. So he says the following about this model, this probably approximately correct model. It's literally the subtitle of his book, Nature's Algorithms for Learning. So this is not like some schmuck who's just saying it. This is like the guy who basically invented machine learning is saying this is the model that nature uses. Okay? So let's just see how wrong it is. Right? Just remember, they're all wrong. The one I'm going to show you is also wrong. Okay, so here's the model. You've got data, its input could be images, questionnaires, whatever you want. The outputs may be disease status. I happen to do biomedical research, so it's often diseases. It comes in pairs. Each pair is IID, as I asserted before. That's the assumption. Or we're just going to say capital D represents the data corpus. Okay, now there's going to be a hypothesis. That word may be confusing, but the hypothesis is basically what the thing thinks about the world. So it's going to eat an input and spit out an output. So it could eat, say, a questionnaire and output what it thinks, or it could eat the past flu data and output what's going to be next. There's lots, capital H is a set of H's, and there's lots of possible capital H's that we explore. Sometimes we do deep nets, sometimes we do random forests, sometimes we do linear functions. There's many options. The key in all this learning theory is now there's a learner. What it's going to do is eat the corpus of data. It's going to spit out a hypothesis. And the goal in machine learning is to choose a learner that has a good hypothesis. That's just what machine learning is about. Now I have to define good hypothesis. Typically, the way it's defined is something that minimizes the empirical loss between predictions and the truth. So it could be the sum of square errors. Your hypothesis says, I think this person is going to have cancer. The truth is the person did have cancer. There's 0 error. Or if they didn't have cancer, it's an error of 1. And you sum that up over all of your training data, and now you say, here's my error. Obviously, there's issues of overfitting, or maybe not obvious, but there are issues of overfitting and things like that. So instead of doing that exactly, you try to find something that minimizes the expected loss in the future when you're going to use it. And that's called risk. Okay, so sorry that's some equations, but that's the model. It's as simple as I could make it that I thought would be appropriate for this. With that model, there's a fundamental theorem of pattern recognition, which is essentially a glorified version of that result from the 30s, which says the following. A learner exists with the following property. With enough data, it will select a hypothesis that is probably approximately correct. The other words down there is like slightly more formal, but that's the same thing. That's the deal. If you assume everything's IID, you assume the goal never changes, and you assume you get basically an infinite amount of data, you'll get the answer as good as possible. That's what machine learning is doing today. There's examples of learners with this thing that you may have heard of. Histograms, support vector machines. Yeah, I'm sorry, you have a question?
Going back to that last slide,
Yeah.
do you believe that?
Yeah, the theorem, I believe. I checked. Oh, a lot of people checked. But it's not a good model of the world. Is that what you mean?
You confused me with your answer. You say you believe it, but it's not a good model.
Yeah. It's a model. So there's a theorem based on a set of assumptions. Those assumptions are a poor approximation to the actual world. But if we accept those assumptions as true, the conclusion of this follows. That's just how math works. Like,
So you believe in a bad model is what you're saying.
I believe the theorem, yeah, I mean, just to be fair, 1 plus 1 is also based on a model. Like, I can change the axiomatic assumptions, and you get 1 plus 1 equals 1. Like, we operate based on the assumptions that tends to lead to things that are reasonable. And when we get better assumptions, we change. I mean, that's the evolution of science. So this is the working model that we have had for 100 years, and it works insofar as AI does whatever it does now. And it's a shitty model. Just both. Yeah.
Got it.
Okay, cool. Thanks for your question. It was a great question. Okay. Examples with this property, you may have heard of some of these things. Histograms support vector machines, random forest, empirical risk minimization. Examples that do not have this property, linear regression, and importantly, deep networks. I just like putting this up because people think like deep networks are so great. But like, they really don't satisfy the fundamental theorem of pattern recognition yet. Like, they are working really well. It's just not exactly clear why. Okay.
Jovo,
Yes.
what's a deep network?
I don't know, how do you want me to answer that? You want me to explain that?
Just a short description.
Oh,
for
okay,
anyone who
great.
Isn't an AI special?
Yeah. So in the 70s, a bunch of cognitive scientists and computer scientists realized that you could do the following thing. You could take an input function, and there could be an output function, and there could actually be a number of them, number of the input functions. And the output would just be a linear combination of the inputs. Really nothing else. But they realized there's a way that you can train the weights of that thing to be able to learn a particular input-output mapping. And this was a big deal. Like, DARPA was stoked, IDA probably was involved. I don't know if that existed yet, but if they did, I'm sure they were involved. Really big deal for like a long time until they realized, this is like my favorite result in the world, it can't solve XOR. XOR is literally the simplest nonlinear problem in the world. So XOR is the following. You're given two inputs. You say yes if only one of the inputs is on, but not both and not neither. It's exclusive or. So it has to be, if the two inputs are like me and Jana, if I say yes and she says yes, it's a no. If neither of us say yes, it's a no. If only I say yes, it's a yes. If only she says yes, it's a yes. They proved that perceptrons cannot solve this problem. And that led to the first AI winter. People were very sad. But a few years later, about a decade later, some other dude realized that actually, if you put a bunch of other neurons, they're called neurons, it's totally nonsense. But anyway, if you put a bunch of functions, just slightly nonlinear functions, in between the input layer and the output layer, called a hidden layer. It's not really hidden, we can all see it, but whatever. Anyway, if you put those in, you only need one or two of them so that you can now solve XOR. And then people subsequently realized that if you put a lot of them in, you can actually represent any function. So there's results from the 89 by Hornick and Chebenko that said you can approximate any function with multi-layer perceptrons. If you just need one layer in the middle, actually, and as long as it's wide enough, you'll get anything.
Yeah, as long as it's fully connected.
Yes.
That was the big breakthrough.
Yeah, and then the secret downside to that is you can do that, but in practice you have to learn the weights from the data, And what they don't have a proof of is that you can do that well in practice. You hope it, and it turns out empirically it works pretty good. But there's no theorem that using the kinds of tools that we use to estimate the weights that they actually converge to the right answer. So does that answer your question?
Yeah, so the depth is the number of layers.
And the depth is the number of layers. Yeah, so a deep network just refers to any network that has at least one hidden layer, really. They used to say stuff about the number of hidden layers, but that wasn't cool anymore.
Actually, let me just,
Sure.
because I waste too much of my time on this, explaining it to people. There was actually it wasn't a theorem, it was a conjecture that what he said was true. But then it turns out that if you do not use symmetric layers, then more layers can actually learn things that could not be learned by a three-level network that was fully connected.
Yeah.
And that was the big break, but it takes insane amounts of computer power
Yeah.
to get those things to learn if they're deep.
Right.
And that's what led to the conundrum in the last talk about why these things are eating so much power.
Right. Yeah, that's a good point. And last year we proved that you actually need positive and negative weights to learn arbitrary function approximations. So it hadn't been clear yet. So there's all sorts of issues in there. But the one issue I want to talk about is not how power hungry or data hungry it is, but there's no time. I just described the entire framework. There's inputs, there's outputs, there's a hypothesis, there's a learner, there's a loss function. I never mentioned time, right? And learning evolved in organisms that deal with time. For example, the fox that learns at the watering hole, the lion tends to be there around noon, does not get eaten the next day. And the one who doesn't probably did get eaten. Right. So we have to learn about time. Like it's kind of the thing. There's all sorts of things that we're not born knowing when they'll happen, but we can learn through experience when they'll happen and be able to predict them. And it turns out when we do that well, we get eaten by tigers and lions less. Okay, so in my remaining 7 minutes, I'm going to tell you our proposed solution. It's actually extremely simple, but I think it's pretty cool anyway. Maybe it's cool because it's simple. So we changed the assumption. We made it much more complicated. Instead of each pair of data points as ID, they're neither identical nor independently distributed. So now, it can be much more complicated. We're still going to have a data corpus, but now it's basically a sequence rather than just a set of points. So a set of points has a property that you can totally reorganize the points, and it's literally the same set. And it doesn't change the output. So you take all the inputs to your deep network, you change the order that you gave it to them, in theory it gives you the exact same output. Now that's not the case anymore for what we're talking about. Okay, so this hypothesis class is going to eat the same input that you had before, and just what time is it? What time was that data collected? Okay, so now it's a function, but it takes two inputs, x and time, and it's going to output a guess. And the point is, you can add this to anything you want pretty easily. Deep networks, random forests, linear functions, whatever. Okay, yeah. Ike?
Just point out there's two notions of time. There's time and there's duration.
Yeah, right, I'm ignoring duration for now. Everything is kind of instantaneous. So if it happens again later, it happens at that time too. Okay. The learner, it's now going to eat a data corpus, but it spits out a different kind of hypothesis. It's a hypothesis that says what it thinks, what it needs to deal with time also. So it has to eat as time and input. But it's still the same goal. We're trying to learn a good one. But now we're going to say a good one is a good one that minimizes empirical loss between predictions and the truth in the future. So integrated over all the future. So instead of minimizing the instantaneous mean square error, which is what people often do, we're now going to minimize this sum is over the predictions of what we think will happen like tomorrow, and also next week, next month, next year, next decade, next millennium, and after the heat death of the universe also. We just put it all in there. You can have a decaying function, so you don't care as much about billions of years from now. But the point is you care about all future time. And now you might think, like, is that really right? Like, is that how we operate? And I just want to say, like, if anyone's ever voted, I'm sure you didn't vote because it was such an ecstatic experience. Right? You voted because you hoped something good would happen later. right? In fact, eating is another one of those things where we mostly eat because we don't want to run out of food later. And in fact, part of the evolution, people talk about homeostasis a lot, but there's this principle of allostasis, which is that part of the evolutionary principles was that we had to get nutrients before we ran out. If you go get nutrients after you run out, you're kind of screwed, right? It's like maybe one of the most fundamental principles of being a living being is that we have to predict what we're going to need later and get it before we run out. So I don't think it's like an extreme assumption. I think it's pretty reasonable. Okay, so now we did all that, and now we can just prove essentially the same theorem that those other guys prove, which, based on wrong assumptions led to a factually accurate conclusion, but now we have a different one, which is a learner exists with the following property. With enough data, it will select a hypothesis that is probably approximately correct forever in the future. So once we get the parameters estimated, the weights in our deep net or whatever, we're going to be as right as possible forever. So it's a much stronger result. It's also pretty cool. I'm going to show you some examples of this in a sec. So just if you look at the figure on the far left, I did the experiment that I just talked about with coin flips. It was a task that was switching. There were two different tasks. Task A was if numbers were positive, label them 1. If they're 0, if they're negative, label them -1. Task B was the opposite, kind of like the reverse handlebar thing. So now if numbers are positive, label them -1. And if they're negative, label them +1. So what I gave to all the algorithms is 10 samples from task A, then 10 samples from task B, then 10 samples from task A, then 10 samples from task B. Basically for, well, in this case, about 2,000 samples. And we have an algorithm called Perspective Learner that eventually, after about 500 samples, it never gets an answer wrong again. Because what it did is it predicts before it switches to B that it's going to switch B because it learned the temporal dynamics of switching. And therefore, it doesn't have to retrospectively respond to the fact that it's getting it wrong and realize it should switch. In contrast, all these other algorithms follow the leader, which is essentially a glorified version of empirical risk minimization for online. Online SGD, which is basically kind of like probably what Ike was talking about. You have all sorts of algorithms these days where you just keep updating your model. As you get more data, you just update it again. And then something called Bayesian gradient descent, which is like the most recent, hottest continual lifelong learning algorithm in the world that learns that there's multiple tasks and then tries to figure out which task it's in. It does so bad, basically as bad as possible, because by the time it realizes that you're on a new task, I switched the task. So it's always getting it wrong, basically. Anyway, we got it right. We did perfect. These two other scenarios, the data distribution got more complicated, but it's the same deal. I don't really know what perfect is on those because they're real data, but we get pretty good, and the other ones seem like they're not. Now, you might think, well, man, that's really easy. I was like, yeah, that's really easy. The world's best AI algorithm totally failed. So I agree it's really easy and embarrassing for the sake of the field, but we can make it more complicated where now you're not sure whether the task is switching at all. Every 10 steps, it might switch to task B or not, and there's some probability that it switches based on which task it's in now. So that's almost that would be Markov if we did that technically, but we also added another thing that automatically resets every once in a while to make it slightly different. Anyway, the point is, again, we're converging, we'll eventually get to a perfect, other things can't do it, and we can make it more complicated, and the other things still can't do it. Obviously, based on our previous experience with LLMs, they can't do inference, so they're not going to be able to do this. Because I get a lot of questions like, oh, well, isn't ChatGPT predicting the next word? Well, yeah, kind of, but it's not doing this. It can't do this at all. It does terrible at this. So I don't have time to get into that, but I trained these algorithms to try to predict the next sequence, just like I gave you before, and it all does terrible. They're at chance, basically. So in my last 15 seconds, I'll just say, we just added time to the foundations of AI. It's kind of simple. And simple algorithms seem to solve simple problems, even though the fancy retrospective algorithms that other people have developed, including me, by the way, utterly embarrassingly fail. And I don't have time for this, so I'll just say, if you want, I'll give you papers. These are students that did the work, and that's my wife and babies at home. Thank you.